floor is yours. I'm going to close the door and get out of your way.
Okay, thank you very much. It's one of the most fun things I get to do at CEBAF is come and talk to groups of students, high school, college, even 6th grade, 2nd to 4th graders. And I have more fun with slightly older groups who have a little more sophistication. So I'm really glad to be here. And I'm going to tell you a little bit about what CEBAF is all about. Now, let's see how that works. Do these lights in front turn off independent of the other lights?
Well, I mean, all of them turn off except two in the very back. Is that going to be too dark?
Well, can you see this? I mean, to the extent we need to, we can.
Is that too dark?
Probably.
And that's the only choice I have. Is this or this?
Focus. Okay. Most of you have had at least this view of CEBAF if you drive down Interstate 64. I'm trying to give you a more personal feeling for what it's about. In particular, we are here to build a world-class, user-friendly laboratory for nuclear physics and research and graduate education centered around the high-intensity electron accelerator. I have taken the liberty of underlining the only words in that thing that I thought you might not all find as part of your everyday vocabulary. And I hope that by the end of this session, you will understand a little bit more about what those underlined words mean. So there's going to be a smattering of nuclear physics in this talk. It's going to be a smattering of technology and accelerator ideas, how does one do it? And then in addition, if you've got patience, you want to stick around, this is, I understand, supposed to be a lab period, we'll do an experiment, okay, which I've brought my Hot Wheels tracks, my marbles, and my pie plates with me. Your experiments always use Hot Wheels tracks, pie plates, and marbles, isn't that correct? Anyway, you're chemistry students. I understand most of you are bound for some other profession than chemistry. However, you should think of nuclear physics as a possible spare time activity. This program was advertised in comic books in the late 50s when nuclear physics was in one of its heydays. And it promised a program that could make you into a nuclear physicist in 14 weeks. Now here we should be able to do in much less that time. Perhaps 14 minutes will do in the nuclear physics part. But there'll be a test next week. Anyway, put yourself in position of Max, the timeless scientist, who is looking, if I'm in people's way, let me know, who is studying matter, homogeneous mass. Note the scale. That block of green stuff he's looking at is only 10 to the minus 16th inches big. That means a few trillionths of an inch in size. A small thing, poor Max. He's having a hard time fathoming it. However, in a way, that is the problem that nuclear physicists and high-energy physicists face. Because this is a brief introduction into the structure of matter. Now, matter, piece of aluminum foil you're all familiar with, it's made up of atoms. Atoms were discovered in 1807. There's a concept invented by the Greeks many years, about 2,000 years earlier, that I ought to be able to tear this piece of aluminum foil in half and half and half and half and half and half and half many, many times. And pretty soon I get to something and I can't tear it in half anymore and it's still aluminum. Okay? That's the atom. Smallest thing I can't break in smaller pieces. Now, this piece of aluminum foil is relatively thin, you'd say. 250,000 atoms thick. So atom is quite small, okay? Now, poor Max, he's looking at smaller things than something that you fit 250,000 of stacked up in this piece of aluminum foil. Just to give you, now the atom isn't the smallest thing there is. The atom is made out of electrons whizzing around in a cloud and protons and neutrons crammed together in the nucleus in the middle. You all know that, right? Okay, well, it turns out, how big is the nucleus? Well, if I took each one of these atoms inside this piece of aluminum foil and blew each one up so it was a mile across, that's big. The nucleus is about the size of a golf ball. Many of you are probably fond and familiar of golf balls, right? One golf ball, 1 mile, okay? 250,000 miles in this thing. One golf ball, the center, that's the nucleus. If I blew up this aluminum foil like that, it would go from here to the moon in thickness. Got it? And the nuclei are little golf balls, spaced about every mile. So if you want to be a nuclear physicist, poor Max, you've got to look at these little golf balls inside of a mile, except it's not a mile, it's a piece of aluminum foil. Small stuff. But the nucleus isn't the smallest thing, as you all know. They're made of protons and neutrons. And the protons and neutrons, they're not the smallest thing either. Back in 1968 was discovered the quark. Okay? Quark is smaller still. Nobody knows yet what's inside the quark. That's what part of what people are thinking of, building this superconducting super collider, 53 miles around. All the states want it. You know, not all the states are going to get it. North Carolina is in the competition, so is Tennessee. That's what people want to build that machine for, so they can find out, is the quark the smallest thing, or what's inside the quark? Because as we've gone through history, okay, between the Greeks and 1807, the smallest piece of matter people could conceive of was the atom. What I have left is the smallest piece is still aluminum. Between 1807 and about 1900, they still thought that was the smallest, but they were starting to get some data that didn't make any sense. 1911 was discovered the nucleus. Aha! We have the new smallest thing. Okay? But lo and behold, it turns out that's not the smallest thing. That's like a clump of marbles. It's made up of nucleons. And now, that was the smallest thing. When I was in elementary school, the smallest thing was the proton and the neutrons. But now that's not true anymore. Now there's smaller things inside of it. And just to give you a feeling, if I took that golf ball and I blew it up so it was a mile in size, the quark would be the size of a golf ball. But that's too fine scale for us at CEBAF. We're interested in the nucleus, the protons and neutrons, and generally how the quarks fill in there. What do you all know about quarks?
Nothing.
You want to know something about quarks? Be the first on your block to know about quarks. Well, first we'll do the lesson. Remember about the golf ball. Well, this is like a proton. Green. Well, it's the wrong color, but a green proton, okay? Can you look inside my proton and tell me what you see?
Something moving around.
Yeah, those are the quarks. I can pop it for you, and then I'll pass around the quarks. So you see, it's a little big thing that I thought was so big and balloon so solid. Turns out it just has these little three things inside it that are quarks. So now, have fun. Anyway, all about quarks. Quarks are right now the most fundamental small particle in the universe thought that matter is made up of. This is my pointer. There are 6 flavors of quarks. Up, down, bottom, top, charm, and strange. Only 5 of them have been discovered for certain, but 6 are predicted by theory. The top quark has not been discovered yet. None of these quarks have been seen by themselves. Okay? They're so tightly connected to each other by the strongest force in nature. None of them have been seen by themselves, and you just get evidence that they have to have been there from circumstantially, okay? But pretty convincingly. Physicists get evidence, they analyze, they say the only explanation possible is there had to be an up quark there. Okay? The normal quarks are up and down. The other ones are sort of more exotic flavors, okay? It actually should say 3 colors. I don't know why it says 6 colors. Well, there are 3 colors of quarks. Red, green, and blue, let us say. Okay? And they're anti-quarks for each kind of quark. Each anti-quark has anti-color, is anti-red, anti-green, and anti-blue. If I want to make particles, I can make a proton by sticking 3 quarks together. 2 up quarks and a down quark. I'll tell you something about quarks. What's the charge of a proton? +1. The charge of a up quark has a charge of +2/3. And a down quark has a charge of -1/3. So I put 2 plus 2/3 together. I get 4/3 minus 1/3 equals +1. Wow. How would I make a neutron out of 3 quarks? Right. Neutron has 0 charge. Excellent. Okay? 2 down and up. Now you made a neutron. Now there are also objects called mesons, which are even more exotic. They have a quark and an antiquark. Always the same color, but it can be a different flavor. Okay? And you make the world this way. Little building blocks, little red, green, and blue, ups, downs, bottoms, tops, stranges, and antis. And we can put the whole particle zoo that the world is made of, the commonest things being protons and neutrons. We can make the world out of them. It's like having little blocks, playing with Lego bricks, okay? You get the 8-thing Lego brick and the 6-thing Lego brick, and you can make houses, cars, whatever you want. Well, that's the way quarks are. And that's the most interesting stuff. That's the most fundamental stuff about quarks. I think I was going to say something else, but I forgot. Oh, the thing about quarks is that you only find them in particles, 2 at a time, or 3 at a time, or some other number at a time. If I had these protons, supposing I say I want to find out about the quark. So I reach into the proton, and I grab one of them, and I pull and I pull and I pull as hard as I can, okay? And suddenly it pops out. So I open up my hand, and I look inside. I was grabbing that green one, okay, the green up. I say, whoops, I've got an up and an anti-up. Got it? That's what I got in my hand. It's a meson. That's what I have. And I look back in that proton, and there's an up, a green up, and a down. The energy that I put in to this proton, trying to pull its quark out, turned into new mass. Einstein's law, energy equals mass. I put energy in, all my muscle power, right? Much too hard for me to pull, though, but all my muscle power I put into this, and I got 2 new particles, a new quark and a new antiquark. So now I have 2 and 3. Shucks, try again. Grab it and pull out. Every time the physicists do experiments like that, they only get out 2s and 3s. They put energy in like crazy, and they just keep making more quarks and antiquarks. So they have not been able to see a quark all by itself. Okay? But they still know it's there. It's interesting, huh? So anyway, you think about the nucleus that way. Here's a slightly different version of the nucleus where I've blown up the protons and the neutrons. I now know that they're balloons. They're sort of fuzzy balloons with little things inside of them. And now the idea of them overlapping becomes, can protons and neutrons overlap? And what happens if they overlap? If I'm looking at this nucleus now, the protons and neutrons aren't marbles. They're these particles with detailed personalities of their own based on the quarks. And a carbon nucleus, which this is, has how many protons and how many neutrons? Anybody remember? You can look in the back of the board if you want to.
That's about a carbon.
12 altogether, 6 of each. 6 protons, 6 neutrons. How many quarks is that? 36. 18. 36 quarks. It's now much more complicated. It's got 36 things inside of it instead of only 12 things inside of it. And those, they can group themselves in different ways. So nuclear physicists, when they were just thinking of a marble proton and neutron nucleus, they had a very simple nucleus. Now they've got a complicated nucleus. But the problem is they don't have any tool available to help them study what's going on in there. And this picture shows what happens. How do you study what's going on in there? Well, you can't just reach in and grab stuff and pull it out. It's too small. You can't take a microscope and look in. It's too small. What you do is you basically build an enormous, very powerful electron microscope. You send little electrons whizzing in, and you watch them bounce out. And maybe you watch pieces of nucleus bounce out. And you collect evidence of something had to happen in there. The electron went in this straight line, and it came out in that direction. A proton came out over there. This has this energy, it's going this way. This has this energy, it's going that way. What had to happen in there when the electron collided with a piece of the nucleus? Okay, something had to happen, and by collecting this data that comes out, lots of it. I mean, one electron and one proton flying out isn't enough to deduce anything. They have to get tens of thousands of events, do statistics, okay? They can figure out what's going on inside of the nucleus. And the little experiment we're going to do later is going to be kind of simulating that nuclear physics experiment, where you will be, I have hidden shapes, and you'll be rolling marbles at the hidden shapes, and you'll be able to figure out, by how the marble bounces out, what the shape is under the plate, even if you don't look at it. Okay? So the problem here is to send electrons in, collect the outgoing electron, collect the nuclear fragment, the proton, or this 6-quark overlapping thing might fly out, something might fly out. Whatever flies out, you want to collect it. Because if you just collect the flying out electron, there's, you're missing some evidence. It's like having a dead body and no gun, or it's like having a gun and no dead body. If you want to be a detective and solve the crime, you want as much data as you can get. You want everything. It's a fired gun doesn't even mean anyone was killed, Could have been used for target practice or something. So you want all the evidence you can get, and that's how the nuclear physicists do it. What I'm going to show you here is kind of how we what one does. One puts a little target right in there, sends electrons through in this pipe, and has two things. They're called spectrometers, but they are multi-hundred-ton magnets for steering the particles. This one steers the electron that comes flying out into a detector attached to a computer over here. This one steers the proton that comes flying out into a detector attached to a computer over there. There's a physicist in a building nearby with the computers attached to his little screen, and he can watch it, he can collect the data, okay? And then he gets tens of thousands of these, and pretty soon he figures out what's going on. That's what we're trying to do. But where do I get the electrons from? Okay? Well, poor Max, he's looking at, remember Max back there? He was looking at that piece of matter, trying to figure out, he says, aha, I can beat it. If I beat it, then I can figure out something about it. So he's building and operating the first big accelerator, which is himself, sending things, beating up on this block of very tiny mass. He's going to find out about it. That's not very sophisticated. He gets smarter, Max does. He gets a better accelerator. It's got better collimation, more aim, and he gets more reactions, okay? But sort of conceptually. So we need to look in the nucleus. What do we need? We need electrons because they probe quarks. It happens that electrons and quarks interact very selectively and in a well-understood way with each other. We want to look inside the protons and neutrons. That's quite a small scale. That's inside the golf ball, inside the mile, inside the aluminum foil, okay? Small, so you need a high energy. Turns out, the smaller the thing you want to look at, the higher the energy you need. The superconducting supercollider has 20 trillion electron volt protons. It wants to look very, very tiny. We only have 4 billion electron volt electrons, okay? So they are looking tinier than we are. They have higher energy. In order to get higher energy, you need a bigger machine to make it, turns out. So interesting thing is the smaller and smaller thing you want to look at, the bigger and bigger machine you have to build to do it. We want to collect all the evidence, the scattered electron and the nuclear fragment that gets sent out. So we need a continuous beam. With a pulsed beam, we would have problems trying to do that. We want to collect data for rare events, rare things that happen inside the nucleus, 1,000 times faster than an existing machine. That means we need a high current. That means a lot of electrons coming, as opposed to a few electrons coming per second. It's this combination of features that makes CEBAF unique. CEBAF is the only accelerator in the world with the properties it has that's designed to do this kind of physics, learning about the structure of the nucleus in terms of the quarks. Just to put a some, put this in your terms you can understand. And if you remind me at the end of class, I've got some brochures I'll hand out. You can take them home that have some of this information in it. Our energy is 4 billion electron volts. What does that mean? That means the electrons are going 99.9999997.8% the speed of light. That's pretty fast. The current is 200 microamperes. That means we have about 1,000,000 billion electrons in a second hitting our nucleus target. The duty factor is 100%. That means electrons come in a continuous stream rather than coming, as they do in many accelerators, in pulses. There might be a pulse 1,000,000th of a second long, then nothing happening for 1,000th of a second, and then you then have another 1,000,000th of a second long pulses, very short pulses, which means that you have a hard time. You're wasting time. I mean, if you want to collect data, why waste that 1,000th of a second in between? Highly inefficient. So you want to spread them all out so you can be collecting data at a convenient rate, lots of them, because you want 10,000, 100,000 events to look at. So how do we make electrons going 99.999, et cetera, percent the speed of light? That many of them. Do you have any? Well, we could use a 4 billion volt battery, for instance. Go down to the hardware store, pick up a couple of dry cells, well, quite a lot of dry cells. But the trouble is, you can't make a 4 billion volt battery. So we have to use, we're now going from nuclear physics to accelerator physics, okay? Just to make sure everybody has the topic straight. Chemistry we left way behind. We use waves. These waves are electric field waves. And what happens if I have an electron, it has a charge, a negative charge. If I put a plus charge over here and a minus charge over there, which way is the electron going to go? It's in between. It's towards the positive, right. And it's going to go faster and faster towards the positive. It's going to accelerate because there's a force on it, okay? So now this electron is accelerating towards the positive. Now it gets there. Now we've got a problem. So what I quickly do is I turn it to 0, let the electron keep going, turn this to negative, and put another positive over there. So now what happens to the electron? It's attracted to that one. And so what I'm doing at any given place in the accelerator is making the electric field oscillate between positive and negative, positive and negative, positive and negative. And as I do it, I'm sending the electrons through in phase. So as they get into space, as the electrons get to this hill, they get right there. This becomes a hill. The electron rolls down accelerating. This is sort of conceptually. Gets to that valley, it would stop. We don't want that to happen. So we flatten it out. So it just coasts along. And we make a new hill. Okay? So now the electron rolls down to the next valley, which we then flatten out by the time it gets there. Now we do this at a radio frequency, 1.5 billion cycles a second. So we got to. I mean, light moves, electrons move 3 billion centimeters a second. Okay? And in order, so we have to be oscillating pretty fast as the machine goes along. What do we use to do this? We use superconducting niobium cavities. Now this is one where you won't be able to see it unless I turn out the light. Okay. These are metal niobium devices. We keep them at 2 degrees Kelvin, so they're superconducting. That means there's essentially no resistance in it. Because we're putting a lot of power in, and we don't want the power to just heat up the metal. We want it to accelerate the electrons. This is exactly the distance an electron would go in 1.5 billionth of a second. So this is going, this neck is plus, this neck is minus, this neck is plus, this neck is minus, okay? So the electron is in here, it's accelerating to there. As it gets to that neck turns neutral, lets it pass through, then that neck turns plus, and this neck turns minus, okay? So each time it goes through one of these kind of donut-shaped things, they're called cells, it gets a kick. Kick, 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 kick. 1.5 billion kicks a second. What we have in our accelerator is 418 of these things. And the electrons get to go around 4 times, so they get lots of kicks. 5 kicks per each of 418 things. I don't know, that's 2,000 kicks around, and 4 times around is 8,000 kicks. Doesn't even take very long to get through, since each kick only lasts 1.5 billionth of a second. Or it's about 2/3 of a billionth of a second. Okay? That's how we accelerate it. Put power in, make those fields, and I'm going to show you schematically what the machine works. We have those things, those cavities, in blue. They're not really blue. They really look like stainless steel. Cryostats. Those cryostats are filled with liquid helium at 2 degrees Kelvin to keep that niobium superconducting. Power comes in the red things. And there's a whole string of these, 200 over here on this half of the accelerator, and 200 over here on this half of the accelerator. We make electrons in the injector. I'll get to that in a minute. Send them into this machine, this LINAC, linear accelerator, LINAC. Accelerate them to 500 million electron volts. Make them go around a corner. Get them in the next LINAC, another half, so now they're going 1. We go back to this beginning again, hit them 1 to 1.5, 1.5 to 2, 2 to 2.5, 2, Then they go around 4 times, they're going 4 billion electron volts. That's exactly what the nuclear physicist ordered. They can come out and be delivered to one of the experimental halls. Okay? Now, these guys are going the speed of light. That means when they're being accelerated, they're all going the same, almost the same speed, even the 1 billion electron volt ones, even the 500 million electron volt ones. I just get rid of a couple of 9s, but that's so close to the speed of light that they're keeping step with each other. Okay? Speed and energy isn't the same thing. So the speed is the same, the energy is very different. As they're going around the corner, the high energy ones, it's like race cars, they would spin off the track. They're guided around the corner by magnets. And if magnets aren't strong enough, the electron will spin off the track. The high energy ones want to spin off the track, so you need strong magnets for the high energy ones and weaker magnets for the low energy ones. So when they're going around the corners, we have to separate them by their energy. Separate paths, separate energies. Send them so they can come back in again where they can all go together because they're all going the same speed. On the straightaway, it's speed that matters. On the corners, it's energy. Okay? That's how the machine works. I'll just try to give you a feeling for it. Here, an artist is drawing what it might be like if you're standing in a tunnel next to these stainless steel, large stainless steel vessels. They're about this big around. They're about 30 feet long. I guess one of them would go from about the front of the classroom to the back of the classroom. And they've got waveguides on it. The tunnel is 13 feet tall, so it's a little taller than this here. That's what it'd be like. This tunnel is underground. I think I'll show that in a minute. I can show it right now. The tunnel is buried underground. I'm sorry about that. With a building on top of it. Technicians and operators can get to that building to service the power supplies. And yet the tunnel can be there because when the machine is operating, we can't have people in the tunnel next to the machine. There's radiation, potential radiation hazard. So here's a tunnel underground, about 15 feet underground. Here is what approximately would look like if you were flying over in a helicopter along about 1993. You would see 3 large experimental halls. By the way, these are about 100 to 200 feet in diameter, 60 feet tall inside, and contain these large spectrometers, experimental equipment. You'd see an oval, 7/8 of a mile around, and underneath that oval, then they have these buildings to contain the power supplies, and other buildings contain control computers and various other support apparatus for the machine. I promised to tell you about how you make electrons. People often ask me that. I'm really not an expert. But you get electrons out of a cathode. You've got a TV set that has a cathode. A cathode is just a thing that gives up electrons. Right? I mean, that's all a cathode is. I'll pass this one around. Be careful with it. You look inside. This one has actually gotten damaged by the guy who was working on it. It's a real cathode. We could have used it in CEBAF. It's one of the 4 or 5 we bought for the electron. You put this is held at a high voltage, 100,000 kilovolts, 100,000 volts, I mean. 100,000 volts you hold this at. Then you put a little bias voltage on it. It works sort of like a vacuum tube. Put a little bias voltage on. That bias voltage controls the amount of electrons that come off, the rate the electrons come off. And they come off. And there's a little tiny thing in there, and the electrons come off, and then they come out this hole in the front. And so this is just to protect it. Has to be in a vacuum to work right. You bolt this on to the container that holds it at 100,000 volts. Then you fire it up. That's all there is to it. So I'll pass this around. I don't know why this doesn't stick together anymore. Okay, I'll just pass that part around. You can all look at it, see what electrons come from. Now, there are an awful lot of electrons in that, so that might last quite a long time, because in how much is a mole?
1 gram atomic weight.
How many atoms are in a mole?
102 times 10 to the negative.
10 to the plus 23rd. So if I don't have hydrogen, supposing I have tungsten, supposing that's a tungsten cathode. Tungsten has how many electrodes? 74. 74 electrons. If I had 74 grams of tungsten, I'd have 74 times 6 times 10 to the 23rd electrons. I don't have 74 grams. Probably have 74 milligrams. But I still have 10 to the 20th electrons. And 10 to the 20th electrons is a lot. Even if I'm using them at a million billion a second, I still last an awful long time. Okay? So it doesn't take very much material to make a lot of electrons. Here is an aerial photograph of the CEBAF site. I'm going to have to turn out the light again. With the accelerator painted on it, as it might be. We're in a building right there, the Virginia Associated Research Campus, and some of you may have been there before. This is the NASA cyclotron building on Jefferson Avenue. Oyster Point meanders through here, and Jefferson Avenue goes right down here. This is the Beaumark missile site, where the city of Newport News parks its school buses. And here you see experimental halls, accelerator, and some other office building we're planning to use a dormitory. And that's what the site, and the site's cleared. You see the cleared area where the accelerator is going to be going. This picture was taken around Thanksgiving time. Just to give you a little bit more, does that come out well enough? You see that? Here are two of those cavities. They're all decked out with all the things they need to work inside that liquid helium vessel, inside that liquid helium bath. Here they are sliding into it. It's just to show. I mean, we've been doing this summer. Here's the enclosed. You can't see the cavities anymore. They're enclosed in what will be filled with liquid helium. The helium will come in that tube. But then you have to insulate it, because 2 degrees is not compatible with room temperature. 2 degrees Kelvin, room temperature is about 300. So you put lots of space blankets, mylar insulation around it, jacket it all up. Then you stick it in another vessel, and then you have a well-insulated cavity that the beam can just come right through, being accelerated. Just to wrap up the talk part, we are being built by the Department of Energy. Our accelerator is scheduled to cost $265 million to build, and it is being paid for by the U.S. Department of Energy. We right now have about 210 people working at the site, some of whom are also students at Thomas Nelson or have been students at Thomas Nelson. And we're planning to have something like 350 people in 1993 when we're finished building in terms of operating the machine. We are a research laboratory, a national research laboratory available to any qualified researcher from across the country, in fact from around the world. any nuclear physicist wanting to do the kind of research you have to do, that you need CEBAF to do, will be able to submit proposals, and if it's a good proposal, they'll get to come and do research. However, we have a special relationship with 38 universities in the southeastern United States who have banded together to form a consortium called the Southeastern Universities Research Association. And these universities, this consortium of universities, manages CEBAF for the Department of Energy. They are a legal entity. We're not a legal entity. We're just a laboratory. We're part of the Southeastern University Research Association. And many of you probably are familiar with several of those schools. You know people who are going to some of those schools. And we've got pretty close ties with those campuses. Anyway, that is all I have to say. Do you have any questions? Yes?
What was it about this area that attracted this facility?
Ah, that is an interesting question. The way physics facilities are developed, it takes many, many years. And usually it's an idea that one physicist has. Gee whiz, we've discovered the quark. I wonder what we need to study the nucleus, understand it better in terms of its structure, in terms of quarks. And that kind of thinking was going on in the early 1970s. In the mid-1970s, sort of the leaders in the community said, well, what we really need is a machine that has these features. But no one knew how to build one. And in 1979, a physics professor at the University of Virginia said, sort of, darn it, I'm not going to wait for somebody else to do it. We've got to get this machine going. My research is going to stop pretty soon if I don't get another tool to push understanding a bit farther. So I'm a nuclear physicist, but I'm going to design a machine. So he held a meeting, and he invited people from around the world with ideas on how to build electron accelerators to come. They came. He got some ideas. He hired some other people. He got support from the governor, got money from the governor, used the research grants he had, put together a design for an accelerator, which he sent to the Department of Energy. He says, you guys, your planning documents say you want to build a machine like this. Here's an idea. Okay? That wasn't the end of it. That was 1982. They said, hey, that's interesting. And anybody else have any ideas? So the Department of Energy collected 5 separate ideas from Massachusetts Institute of Technology, from Argonne National Laboratory in Chicago, from the National Bureau of Standards in Washington, D.C., from the Southeastern Universities Research Association, who had formed by that time, and from sort of centered at UVA, and from the University of Illinois. Okay? Most of these places already had accelerators of a different sort. They were building, operating, running, and they had a lot of experience. The University of Virginia group was sort of a black horse among them. The Department of Energy says, hey, now we got 5 proposals, and they convened the committee to help them evaluate those proposals. That committee recommended that the proposal from the Southeastern universities be accepted, be the one that's funded. Now, it's still not that simple. That's 1983. We didn't get money to build the machine until 1987. By the end of 1984, SURA had a contract with DOE to do research and development work, preparatory furthering the design. Okay? And SURA, the governor of Virginia had been very supportive. The legislature had been supportive. So it was going to be in Virginia someplace. SURA, when DOE said, okay, we're going to build yours, where are you going to build it? They had to figure out where to build it, and there were several sites. There was a site in Charlottesville, there was a site near Petersburg, there was a site up near Dulles Airport, there was a site near Blacksburg where VPI is, and then there was a site down here, which particularly Old Dominion University and William & Mary were championing and putting forth because it would be convenient, very convenient to them. And it turned out, all things considered, geology, ease of getting the land, credibility of the offer, that the Newport News site, which the city of Newport News promised to give to the Department of Energy, so they had to put out the money to get it, was the one that was selected as the place to build it. The city and the local community has been, in fact, wonderfully enthusiastic. The city has put out a lot of money, namely something like $3.5 million to buy this site, the parts of the site that didn't own already. And they donated 40 acres that they did own already that they didn't have to buy separately. But I mean, the land was there, the availability of the NASA building. The state said you can use this administrative building, the VARC building, for the life of the project for $1 a year lease, or there's a formal lease agreement between SURA and the state of Virginia. And all those things thrown together made for a very attractive site. The proximity to the airports was important. The proximity to high-tech resources and experience of NASA, the NASA contractors, the shipyard contractors, and the universities, ODU, William & Mary, CNC, Thomas Nelson, the whole works. It made it a nice area, okay? And that was all weighed in the selection, and so now we're here, and we've brought several hundred other, 200 other people here too.
Thank you.
It's probably more than you wanted to know.
Okay.
But it's kind of interesting to see how physics projects get, and it takes a long time. 1976 was the first time there was a really clear call that we need a machine like this. It takes until 1987 before we have any money to start building it. A patient community. I mean, and it's going to be until 1993 before anyone can use it.
So what did the professor do at UVA?
He's a physics. What did he do?
Yeah, he said he needed something continuous research.
Yeah.
He showed it to me.
Well, there are accelerators at Stanford, at MIT, that have slightly different features. You can't do some of the experiments as well. You can do different experiments. You can do background experiments leading into it. He's involved helping plan experiments at CEBAF, which takes a lot of effort, a lot of time to put these big pieces of equipment, to get them optimized right, to get them ordered and designed, and doing some experiments in the meantime at these other places. But he sees it coming on the horizon, and he's only got a 2.5-hour drive to get here. Okay? Everyone want to stretch their legs a few minutes and come back for lab?
Take like 5 minutes.
I am going to let you now that you've had your 14-minute nuclear physics and 25-minute accelerator technology and physics lecture, and you're all experts, you're going to get to be nuclear physicists for a moment. I've brought my children's toys, some of them. I have some Hot Wheels tracks and some little joiners. I'd like to ask you to get, I have 8 sets, okay? And I don't know how many people in the class, but it looks like it's about 2 or 3 people per set. What you do is you get 3 Hot Wheels tracks, you get 1 marble, 1 shooter, and 3 joiners, and I'll come around and give you plates later. And you also get 1 lab sheet, okay? You will take your Hot Wheels tracks and make them into a loop. The Hot Wheels tracks, you notice, also have lines on them. Those lines are to kind of mark direction. And the pie plates with shapes under them have compass marks on them: north, south, east, west. So what I'm going to do is take my pie plate and set it down here with north pointing toward one of the lines. Then there's 2 other lines, and then west comes next, so that I've kind of divided the circle into several angular directions. And now I can shoot. They say come in from this. I can shoot with my marble. Whoops. Right. And watch it come out. I shot from the straight south, and it came out almost toward me. I shot from just off to the south, and it came out at a strong angle. I shot from just this side of the south, and it went straight through. So now I know that my whole shape is on that side of south. Now the question is, what happens if I shoot from the east? It comes straight back. I shoot a little off east. It also comes straight back. I shoot a little off east. Okay? So I would say that my shape has a straight line perpendicular east, because I was moving my shooter back and forth, and wherever I shot from this side, east, it was a straight line. If I shoot at an angle from sort of the east, it comes off at another angle, okay? Now I'm going to pass out shapes. I'm not going to tell you what they are. I'm only going to tell you that each shape has only flat and round sides. Okay, nothing fancy. I do have a fancy one. If anyone wants to try the fancy one, I had a nuclear physics PhD candidate work on it for 3 hours and he got the answer. He had to roll marbles for 3 hours to figure it out, though. It's a very complicated shape. The other shapes you ought to be able to do in a few minutes. The idea, generally, is probing. I mean, you're sending things in from different angles, and you're watching them come out. You see where they come out. The idea is generally to shoot them in either tangent, I mean, perpendicular to the edge of the circle, okay? Or you shoot them in from a direction, along one side, and then you can shoot it from another direction along. That way you find out if you have straight or curved edges and which way the straight or curved edges are oriented, okay? Now, I want to say one other thing. What do you suppose I'd find out if I used a basketball to shoot instead of this marble? I'm now not going to roll my marble. I have my pie plate here with the shape underneath it, and about a ½ an inch between the lip of the pie plate and the table. What happens if they didn't give me high energy marbles, high energy electrons? They give me low energy electrons that are the size of basketballs. And I started rolling my basketball at it. What would I find out? I could maybe find out I had a pie plate. It might just roll over. Okay? If I had a tennis ball, I'd for sure find out I had a pie plate here. Supposing I used the BB to roll out. It's an even higher energy particle. Okay? Well, I'm telling you I have straight sides, but if in fact I used a saw and it had jiggly edges, the marble isn't going to see those little jiggly edges in my, say, if it's a piece of wood under there, let's say. But if I use the BB, it might. So you see how the different energy or size of the probe, if I use a basketball or a softball or tennis ball, I find out about the shape of this plate out here. If I use a marble, I find out about the shape of the hidden shape. And if I use a BB or something even smaller, I find out about the details of these flat circles, these flat sides and circular sides, okay? So that's how the different energy of the electron makes a difference in what it can tell about what's going on in the nucleus. I use a low energy electron, I can tell I got a nucleus there. That's how they found the nucleus, in fact. Because low energy electrons were just bouncing off of something, sometimes coming straight back toward you, when you sent them into a piece of aluminum foil or gold foil. Anyway, so please, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Looks like we can have about 2 people per pie plate. Each pair of people wants a table. Okay? So can you make yourself in pairs and send one person up? I'll have to give out mine here. So here's one already made. Here are some lab sheets.
Yeah, all right. You can draw on this.
This is what it's
I
for.
really
I'll record it.
We don't know what it is. Yeah, but we're not sure exactly what it is.
Okay, then it's good. Wait a minute, get this out now. When you rolled it in from, came straight back. You rolled it from the south. Came straight back. When you went in from the east, you're going from.
I look now, I think I know what I got.